Okay then, so this is a talk on spectral methods and some applications of them in for numerical purposes, as in for differentiating and integrating and solving partial differential equations using a computer. Now, basically, we're going to be talking about sort of Fourier methods. Excuse me. So generally, spectral methods involve thinking about how some function can be expressed as a sum of a series of other functions weighted by things. So you might use polynomials of higher and higher degree, and then you'd be talking about something like a Taylor series. Or you might use sine and cosine waves of higher and higher frequency, in which case you'd be talking about Fourier methods. You might choose other sorts of sets of functions like Chebyshev polynomials or what have you. But we're going to be focusing upon the sine and cosine things because that's sort of the core of what most people consider to be spectral methods, because it's been very well studied and those kind of things have a lot of nice properties, especially for numerical methods. So a basic overview of what we're going to do. We're going to look at how, in a sort of practical way, in a computer, you can represent a function, or let's say a sort of sampling of the values of a function at discrete points, how you can represent that data or approximate it as a sort of something like a Fourier series or a truncated Fourier series, how that kind of approach helps you to do differentiation. So I call this the derivative theorem. It's basically, if you have, it's this sort of, it's a spectral method based solution to this sort of age old problem of, if you know what a function is doing at certain points, how do you calculate its derivative at those points? And so that's basically our application to differentiation. There's also the application to integration, which is given by this convolution theorem. So basically it turns out that there's a certain class of integrals called convolution integrals that, using spectral methods, gives us a much faster way to, and more accurate way to evaluate than using the standard sort of numerical integration techniques. So okay, let's go. So let's suppose that g is a period L function. So we're going to do this quite a lot, and as we go on and we think more about numerical methods as well, you might start to wonder how sort of does this assumption cramp our generality? And it kind of does in a way, but there's often quite a few sort of hacks we can do by padding some zeros and thinking about things being periodic in places where we're not interested in them, so that we can often treat things which are not periodic as if they were periodic, and then we can apply all of this kind of theory. So anyway, our initial assumption is to suppose g is a period L function. Now I'm just going to start off with, for the first few equations, they're not going to be anything we're going to use. I'm just trying to give a bit of sort of background of how, well, I want to have a bit of continuity between the standard sort of Fourier series notions and the kind of sums we're going to be working with. So we'll assume that g has so g's going to have a Fourier series as long as it's reasonably well behaved. And we can write it like this. So basically it's a sum of sines and cosines. Now if you look at the argument of, say, this sine function, it's 2 pi divided by L times x times k. So think of it as a function of x. If k was equal to 1, then that sine wave would have a period of L. In other words, it would take L to do a complete oscillation over space, x. So then what k is what's called the wave number. So basically k is the number of waves which fit into that interval, say from 0 to L. In fact, since it's a periodic function, it's you can take any size L interval and you'll have k waves fitting in it. So basically we have this sort of thing, and this is the core of how we're thinking about these functions being expressed. Basically, and what the AKs and BKs are sort of weights that we're attributing to these different waves. So we're imagining our function is made out of waves of higher and higher frequency given by different weights. And this is just a certain sort of family of functions that we can sort of add together in a weighted way to represent what our function is doing. Turns out there's some fairly good reasons to pick this particular setup often, but there we go. Anyway, here we have sines and we have cosines, and everything's real in this equation up above, but it's a bit annoying to have to always be thinking of sines and cosines. It turns out to be a lot more succinct just to change everything into the idea of complex exponentials. So we use this sort of Eulers formula, e to the I theta equals cosine theta plus I sine theta, and then we can basically use that formula to rewrite what cosine theta and sine theta are in terms of complex exponentials. And if we just substitute those into that formula, then you can see, if you sit down at it for a bit, that we can basically write g is equal to the sum of complex exponentials weighted by some factor g hat k. So you see that the argument of the exponential is basically the same looking as those in the sines and cosines, and sort of this in a way it kind of helps, because it means if we were interested in doing this sort of thing for functions with complex values, we could do. But for today, let's just carry on thinking about a real valued function g. So then, I remember when I first saw this sort of thing, one question popped up was, well, why bother going into the complex domain to sort of think about how to express things which are purely real? And conceptually, there's one could think about things like that, but in actuality, it just sort of makes things simpler notationally. And so now our constants multiplying the exponentials, these g hat things, are going to be complex numbers, but that's not really going to affect anything to do with our algebra. So the point here, so what I want to do basically is to get towards a formula, a sort of truncated sum, a bit like this, which we're going to use practically. So the point here, and this is all very sort of rough and hand wavy, is that these g hat terms, when we're thinking of g hat terms, so g hat k, where k is close to 0, they're going to be pretty significant in determining, in sort of describing the behaviour of a function. So think about Taylor series. The first few terms of the Taylor series are very important, but for a lot of functions, you can discard higher and higher order terms of the Taylor series because they have sort of less impact on what the function's doing. So we have a similar sort of phenomenon here. And so the sort of type of numerical approximation we take is that we can pick some even integer n, positive even integer, hopefully a fairly large one, and we can just truncate that series by throwing away all the terms with an absolute value bigger than n. So then we get this sort of approximation of what g is. So this isn't, we're very close to, but we're not exactly at the sort of form we want to work with yet. So there's one other thing. I mean, how many terms are there in this sum? Well, there's going to be n plus 1 terms, aren't there? N where k is non-zero, and there's going to be an extra term when k is 0. But we actually want to throw away one of these terms. So this is basically just to get our sum into a form which is nice to work with, because I haven't really told you anything yet about how to compute these g hat k's and things like that. So basically I wanted to show you this because you can see in a sort of symmetric way where it comes from the infinite sum, but in order to justify throwing away one of the terms, it's quite useful to see, just to consider this, what's happening with this exponential thing here. So basically what we're going to be doing practically is we're going to be working over discrete points. So x, sometimes we'll think of it as a continuous variable when we're deriving formulae. Whenever we're doing numerical methods, we shall be thinking of x as being sampled from n points, and those points are going to take the form x subscript j, and I use that as shorthand to denote the point j times L divided by n. So basically we want to have it so that we have n points, capital N points, fitting into this interval and uniformly spaced in this interval from 0 to L. We want it so that our initial point is 0. And so basically what we do is we sort of create a step size, and our step size we can think of as L divided by n, the length of the period, divided by the number of points we have. And so an integer j times that step size will give us our point xj, and we'll think of j as running from 0 to n minus 1. So we're basically now thinking of restricting our attention to x values, which are certain grid points, xj. And for such xj, if we have a look at this exponential term, we can see that it has this feature that basically it's periodic in k. What I mean is that if we add n to k, then we get the same thing. So to put it more explicitly, exponential of 2 pi I k divided by L times xj is equal to exponential of 2 pi I k times k plus n divided by L times xj. So we can just check this formula, just expanding it out by writing what xj is, and we see that the inputs to these exponentials just vary by 2 pi I is the square root of minus 1. So to vary by 2 pi I times j. So since this exponential, whenever you add 2 pi I to its argument, you just go a full way around the circle in the complex diagram. If you go an integer number of times round, it doesn't affect anything. So these two terms are the same. So yes, this input is periodic. So this has an interesting implication if we have a look at the formula, because basically this formula involves constants times this exponential, which has a certain constants times exponentials of different types. But I've just said that these exponentials of different types are repeating with period n with respect to k. So if you think of these constants g hat k, essentially we can think of those as repeating too, because it turns out there's going to be a sort of unique way to determine what these constants are. And so, you know, if you forget about the actual value that k is taking, the point is that you're going to have n of these different exponential functions, each of which is going to be multiplied by a constant for a sort of set of n different k values. And where exactly those k values are doesn't matter, because the exponential thing, the sort of basis vectors, are going to be periodic with period n. So the constants are as well that are multiplying by them. I'm sorry, that might not be very clear, but don't worry about it if you don't understand my rambling. It should become more clear later, hopefully. So let's get to here. Yeah, okay, so just want to use that fact just to get our sum into the appropriate form. So basically, when k is minus n over 2, then the exponential has this form. But that's actually going to be the same as the exponential that we get by adding n to that k value. So if we put k equals n over 2 instead into here, we'll get the same value. So basically what I'm saying is, if we look at this sum at the top, the first entry of it, the exponential in that, is going to be the same as the exponential in the last entry. So then why not just group those terms together and redefine these constants gk appropriately? So we can do that, and now we have a sum of this sort of form. Now we have a sum of this sort of form, so we're getting closer to what we want. The only other thing is that, as we've already said, these exponential terms are going to be period n with respect to k. And so what we can do is essentially think of these multipliers, these weights gk star, as also being period n. And so basically what we've been running over I mean, what we're trying to do here basically is to rewrite the formula in this sort of form, so that we're just going to be summing from k is 0 to k is n minus 1, rather than summing from k is minus n over 2 to n over 2 minus 1. So what we can do is just think of these terms where k is negative, and we can write the multipliers. So g star minus n over 2, g star minus n over 2 plus 1, and so on. And the crucial thing here that I've been trying to say is that essentially we can think of these constants g star k as being a sequence which is period n. So we have this general identity that g star of k is g star of k plus n, and using that we can just add n to all the terms of this sequence and get these sort of terms gn over 2, gn over 2 plus 1, blah blah blah, up to gn minus 1. So basically we can take this sum, sort of pull off the terms where k is negative and clip them back on again on the right hand side, and we get this sort of form. So we're almost there. The only one little extra bit of surgery I want to do is just to redefine these constants. So these ones are called g star k, and let's just introduce new constants. We'll define g tilde k to equal n times g star k. So then we can rewrite our function like this. So this is our critical sort of function here. In fact, I'll just write it in terms of general x. So this is written in terms of xj, which xj means x at one of these set grid points, but you can think of this as defined for a general real value x. And so this is our critical formula. And I could have really started here. I just wanted to give a bit of background of where these things are coming from. So basically we have a period L function g, and for some x, gx is approximated by excuse me, it's approximated by 1 over n times the sum from k is 0 to n minus 1 of g tilde k times exponential of 2 pi I xk all divided by L. So basically we're thinking of expressing gx as a weighted sum of complex exponentials. The complex exponential has a sort of wave number which is fitting into the thing like this. So these complex what I meant to say is these complex exponentials have wave numbers which are increasing with the sum. So okay, let's we can express a function or approximate a function as this kind of expression, but what does that mean? Well, it doesn't mean much if we can't calculate what these so-called Fourier coefficients, that's what these g tilde k's are called, these constants, these weights, they're called Fourier coefficients, and we have to be able to calculate those, right? Otherwise this whole enterprise doesn't mean much for practical purposes. So how do we calculate them? Well, it turns out that basically they're given, you can work out what the Fourier coefficients are in terms of the samplings of g on these grid points by a very similar formula to the way that you can approximate the grid points via the Fourier coefficients, a la equation 3. So this is the formula to get the Fourier coefficients, and this is really, I would say this is this is basically the Fourier transform, or the fast Fourier. It's basically what the fast Fourier transform does. So I ought to say so I ought to say what the sort of main motivations are for actually doing this sort of these spectral methods. One of the main motivations, at least, I should talk about is this thing about the fast Fourier transform. So why is it that we want to do integration and differentiation by these methods? And basically it's all about this fast Fourier transform, which, if you're going to convert your sort of basis, if you're going to represent something by a load of other functions weighted by something, then that takes a fair amount of computational effort to work out. In linear algebra, to do that sort of conversion, say for a length n vector, it'll take something like order n squared time. Now, the thing is, with the fast Fourier transform method, we can work out what these Fourier coefficients are very, very quickly in n log n time by this sort of magical algorithm called the fast Fourier transform, which is this thing is abnormally fast, and I would say for this reason a lot of people interested in numerical methods have sort of bent as many of their problems towards the Fourier sort of methods as possible in order to exploit this speedy algorithm. So I've used this sort of fn of g to sort of denote that we're doing some operation on g here in order to obtain these Fourier coefficients. And so the subscript n denotes that we're using an approximation where we're just looking at n terms, and the subscript k on the end denotes that this is basically a shorthand notation for this is a sort of shorthand notation for the kth such Fourier coefficient, the multiplier of the of the k thing. K is the wave number. So basically, in a computer, we'll be calculating that this fn thing will basically be the fast Fourier transform, written as FFT. And what you can see from this equation 4 is that we can work out what g tilde k is, or equivalently this thing written with the f. We can find out what this is from the sum. It's given by the sum over j from 0 to n minus 1. So we're basically summing over these grid points xj, and at each such grid point we're working out what g of xj is, the function at that grid point, times the exponential of minus 2 pi I divided by L times k times xj. So this is basically the sort of this is the way you work out the coefficients, and then the way you approximate the values from the coefficients is given by this equation 3 up here, which has a very similar form, especially when we consider it like it's written at the bottom of this page for a point xj, one of our grid points. So basically we can think of this f subscript n thing as something which maps the values of g at our grid points and then gives us our coefficients out. And as I say, it does it in n log n time, which is fast, order n log n time. Okay, so we have f of n. What about the inverse, f of n minus 1? So f of n takes us from our data points to our Fourier coefficients. What about if we want to go from our Fourier coefficients back to our data points? Well, that's just exactly what this equation 3 is doing. We're just saying, okay, we have the Fourier coefficients, we use those to weight exponentials, and we get a approximation of our values. So that's the sort of inverse. So basically, if we just write that equation again, we can just label it as the sort of inverse of this f transform. So you can think of this f transform basically as something which is mapping the vector of values. Okay, let's go back to equation 4. Yeah, it's sort of mapping the vector of values of g at the different grid points onto the vector of values of the coefficients, the Fourier coefficients g tilde of k for the n different values of k. And the inverse obviously sends you back again, does the opposite of that map. Although actually I haven't proved that yet, so the whole thing I've been talking about so far, about how we'll figure out these Fourier coefficients and all the rest of it, I haven't given you any proof of it, so I haven't sort of stated it as a proper thing. So here it is. Let's call it the inversion theorem. Let's sort of make it a theorem that we have to prove that, yes, if we have a period L function and we have these f of n and f of n minus 1, that if you apply one and then you apply the inverse of the other, you get back to the value of g at your grid point. So, because obviously we want f of n to be the inverse of f of n minus 1. So basically all we're saying here is that if we have something like equation 3 here, then we can calculate the Fourier coefficients by something like equation 4 here. And we're basically just saying it with this inversion theorem that this is consistent. So maybe we can have a quick peek at a proof of that. I think it's a good time to do it. I'm just going to go through it very briefly. So inversion theorem. Here we are. So all we do is we've got our equation 3 and equation 4 on the first couple of lines. And then all we do is we write this formula that we're interested in. We're going to have to work with it at a particular grid point. So we'll work with this supposing that x is equal to xn. So it's we're evaluating x at one of these grid points. And then all we do is substitute in for the formulas. So then we get this rather meaty looking sum here. And so we take the sums to the left because it's all just things multiplied by each other. And then what we can notice, there's a typo here. Is there? Oh no, maybe there isn't. No. Yeah, so we can move the sums to the left. We can these exponentials are multiplied by each other, so we can add their arguments and factorize and things. And so we've got a sum over wave number k and a sum over grid points j. Well, let's just suck up the sum over k into some function, some entry which we'll call zeta nj. So basically all we're doing is substituting here, and we'll just define zeta nj as this sum of exponentials here. Now if you evaluate this is interesting, I think, because this is basically, you think of it, so when n equals j, then this is going to be a sum of n exponentials, but the arguments of those exponentials are going to be 0. So it's just going to be a sum of e to the zeros, so it's going to just equal n. If n's not equal to j, then n minus j is going to be some integer. So what you're going to have is 2 pi I times some integer times k divided by n, but you're summing k from 0 to n minus 1. So there's this sort of formula that sums like that, where you're basically doing something like adding up all of the complex roots of unity, gives you 0. So it's related to this idea that the center of gravity of a regular polygon is the middle of it. If you think of things in terms of what's going on the complex plane. So basically we write zeta nj is equal to n times Kronecker delta nj. Substitute that into our formula. The 1 over n cancels with that n we put in, so we have that our thing's equal to this, and then the Kronecker delta just picks out the value of g of xn. So that sort of proves our inversion theorem. Okay, so we can go back. Where were we? Yeah, so this is an approximation, etc. Okay, so now we've basically got all of our results, and we've had some understanding of what's going on with them. So now, how do we use this kind of stuff for, let's say, spectral differentiation? Okay, so basically, we know the values of G at these different grid points, xj, and so we can use what's it somewhere? Yeah, we can use this equation 4 to work out the Fourier coefficients of it. And then it turns out that what we can do is, so essentially what we're doing here is, you think of it as moving from X space, as in the space where our grid points are in, to Fourier space, where the things in there are the Fourier coefficients. So when we're in Fourier space, we can, there's a sort of easy way to do the differentiation, and then we can just convert back into the X space again by applying an inverse of this Fourier transform thing, as in apply f of n minus 1. So okay, the crucial thing here is that there is a fast way to do this spectral differentiation, and this fast way is basically given by this differentiation theorem. So what it's saying is that, say we want to work out g dash of xj, as in the derivative of g at xj. Well, if we only know what g is doing at these points xj, these discrete grid points, then we're not going to be able to say for certainty what its derivative is, but we can approximate it. Normally one would approximate it using something like a finite difference scheme, but we can do it like this. And what this differentiation theorem is saying is that if we do a Fourier transform on G, so we get the Fourier coefficients. So when we get this subscript k here, we're talking about the k such Fourier coefficient. Now multiply that by 2 pi I k divided by L, and that basically gives you so doing that basically converts you from the Fourier coefficient of the function g to the Fourier coefficient of the derivative of the function g. So then all you have to do is do the inverse Fourier transform to shift that coefficient back into the original space again, those coefficients back into the original space again, and you get this approximation for the derivative. So this is really, really cool, because basically this differentiation method gives something that's much, much faster, that's much, much more accurate than the kind of things you can get away with when you're using endpoints for a finite difference method. And so basically the point is that, let's say you're trying to evolve some partial differential equation. So you have the equation specified at different points in space, and you want to work out how to evolve it in time. You have some formula that you can look at its derivatives in space and get an expression for how it's going to evolve in time. So the usual way you do that is to just approximate derivatives using a finite difference scheme. This gives you a different way to do it, as long as you can treat your function as being periodic in space, and it's like really, really accurate. So okay, how do we prove it? Seems like a crazy formula, but it's actually really easy to prove. So all we do is just look at equation 3, here it is, and we simply differentiate it with respect to x. So we differentiate it on the left, we get g dash of x. We differentiate it on the right. All that happens is that the multipliers of the x fall out of the exponential arguments. So we just have a 2 pi I k divided by L appear here, and then we can just think of that as grouped together with this g tilde k to form a new sort of a new sort of g of differential of tilde. So basically we're just comparing the kind of look of the two different equations and saying, well, if we think of that as our new Fourier coefficient, then everything looks good. And so that's basically it. So remember that g tilde of k, that's just the Fourier coefficients. So we can write that in terms of our formula here, and we've got the proof. Okay, so that's basically what spectral methods does for us with respect to differentiation. With respect to integration, I wouldn't say it always does that much for us, but when we have so-called convolution integrals, it really speeds up how we compute those. So typically, if you have an integral, you sort of have to do a Riemann sum or some quadrature method, but something involving summing up a load of points, and that normally takes sort of order n time if you're discretizing your data, so you've got n grid points. Now let's say you want to evaluate an integral of a function of one variable. So that variable can go over, let's say, n different grid points, and at each of those you have to work out this integral taking order n time. So to work out what an integral does like that, it sort of takes order n squared time, because you have to work it out at n grid points. But convolution integrals have a special nature that means that we can use Fourier methods to work out what they do at all these n grid points in one stroke using some Fourier methods. So what are convolution integrals? Well, basically, there'll be an integral of a function f of x minus y times g of y integrated over some interval. We're going to work from over an interval from 0 to L in this case. So f and g are period L functions. So this is the critical result. This is basically what... So I'll just say, for practical purposes, of course, f and g may not be period L. There may be some functions of finite support, and we may not be interested in their integrals from 0 to L. Another constraint here that we're looking at is that x ought to be between 0 and L. Although actually I'm not sure we need that. But anyway, yeah, no, we're saying that we want to know what this function does for the x between 0 and L, for all of them. Okay, so we have these different constraints, and this is... So our real practical situation may not be like this, and so we may have to do some padding and things like that, so that it looks like these functions, so that we can pretend that our functions are periodic, and then we may have to do some sort of shifting around and changing intervals and changing variables and substituting and replacing functions with different functions in order to get our problem into this form. So sometimes it can take quite some work to change a problem into this sort of form where we can use this convolution theorem. But once we've got it, there's a fast way we can evaluate what this integral, the values of this integral over all of our grid points, xj, between 0 and L, and we can find out what it is at all of those grid points in one stroke. So basically it's given by this formula here. So what this is saying, working from inside the bracket out, is that if we do the fast Fourier transform of f and the fast Fourier transform of g, so those will basically give us like vectors of Fourier coefficients, so g tilde subscript 0, g tilde subscript 1, all the way to g tilde subscript n minus 1. Multiply that by the similar thing with f's instead of g's. So we sort of component-wise multiply those things. And then we do the inverse fast Fourier transform of that, and evaluate that at x, or at the jth grid point if you prefer, and multiply it by the step size, L divided by n, and that will give us an approximation to the value of our convolution integral. So probably easier. So basically, to cut a long story short, basically, to work out a convolution integral like this, you just convert f and g to Fourier space. In Fourier space, the convolution is sort of equivalent to multiplying the Fourier coefficients. Then you convert back into ordinary space, and you have an extra constant, the step size that you're working with, to multiply by. So since it's very, very fast to do multiplication, and it's very, very fast to transform to and from the Fourier space, this gives you a very fast way to work out this integral. But to see the details of it, best to just go through a proof. So if we write g is equal to, we'll just use our equation 3. So we'll write g as a sort of truncated sum involving these Fourier coefficients. So that's g of y. And we also have f of x minus y. We can write that as a sum. And now basically all we do, if we look back at our convolution formula, we just substitute those terms into this integral. It's remarkable how these proofs work in these spectral methods. You just seem to sort of write the substitutions, drop them in, and do a bit of trick. If you know how to rearrange the sums and integrals properly, then there often tends to be some kind of a Kronecker delta that comes in and simplifies everything. So that's basically what happens here. So we have an integral, constant 1 over n, and then we're summing over k and k dash. So when I was writing these things, basically using equation 3, I made sure that for when I'm writing g, I'm summing over wave numbers that I'm calling k. When I'm writing f, I'm summing over wave numbers that I'm calling k dash. So that's so that when I do these substitutions, I can see that I'm summing over different wave numbers with different names, essentially. So we've got a sum over k and a sum over k dash and an integral from 0 to L. So we can rearrange these. Basically, we can do some kind of recombination with our exponentials, sort of rewriting them. And I'll just introduce this this constant psi kk dash, which is given by this integral here, and basically you can see all I've done is move the integral and the terms involving y to the sort of right of the sum, and then introduce this new symbol to package them all together. But that's nice because this is just an integral from 0 to L of some exponential thing times y. We can see when k is equal to k dash, this is just going to be an integral of e to the 0, so it's just going to equal L. When k is not equal to k dash, if you just evaluate this integral, you'll find it's equal to 0. So basically what I'm saying is that psi here is just equal to the Kronecker delta kk dash times L. So if we substitute that back into our formula, then basically we're summing over k and we're summing over k dash, but we're only getting non-zero terms when k is equal to k dash. So that allows us to get rid of one of these sums. And then if we look at the form of this, you can see that it's basically just it has just the same form. Well, it's L divided by n times something which has just the same form as we get in equation 3 for the except we've got the product here of gk tilde and fk tilde, where we would normally have our Fourier coefficients appearing in that formula. So basically, if we think of this as new Fourier coefficients, then what we can say here is that we've basically got L divided by n, and what this expression really looks like is the sort of inverse Fourier transform of this thing with Fourier coefficients g tilde k times f tilde k, evaluated at the point x. So that's what I mean by these square brackets x. And basically we can just go from our tilde notation to our f notation, and then we basically get the formula that we started with. So that proves the convolution theorem.